Let's look at this important problem which we really have not looked so far. A linear combination of jointly Gaussian random variables. So what are we starting with? X and Y are jointly Gaussian. This is where we are starting with. So what do we mean by jointly Gaussian? We mean exactly this. The joint density function of x and y are given by the top expression, or equivalently this is one and the same thing. Remember I told you this is a two-dimensional Fourier transform, or the joint characteristic function of x and y is given by this. So what is the problem? We are interested in the following. I take, remember so far we have been looking at x plus y, x minus y, etc. Let me take a general combination, ax plus by. That's what I mean by linear combination. Question is, what can you say about the density function of z? Or I'll get more greedy, I'll say I'll take another linear combination, cx plus dy. So of course, what is the density function of w? But more importantly, we also want to know what are the joint density function of z and w. So we can solve all this. Of course, you know how to solve this, right? You find the Jacobian, then you put the transformation, you can do that. But I'm going to show you that in this case, we can use the characteristic function to quickly solve for z, for all this, right? And of course, then the question is, are z and w independent? If not, what is the correlation between z and w? All these questions are interesting, right? So let's start with the simple one. So let's try to find out the characteristic function of z. Look here, z is given to be ax plus by. So this is a linear combination, right? X plus y is a special case. X minus y is a special case, right? Put a equal to 1, b equal to minus 1. So everything is here. So I'm going to take this and plug it in here. So this is e to the power j omega z. But z is given to be what? Look at here. Z is ax plus by. So I can write this as what? What happened? So this is expected value, right? So I can write this as expected value of e raised to j x multiplied by a omega plus y multiplied by b omega. So this is the joint characteristic function evaluated where? Anyone? So remember, this is of course e to the power j xu plus yv. So what is this one? Anyone? xu plus yv. So this is a joint characteristic function evaluated at? But joint characteristic function at u comma v is given here, right? U comma v is here. So instead of u, I should substitute what? A omega. Instead of b, I should substitute what? Instead of v, I should substitute b omega. So let me do that, see whether I am doing it correctly. So this is e raised to j yes? So if I substitute for u a omega and v b omega, I get this expression. So look at this. This looks like, if I call this to be mu z, and I know, you know from little earlier we had discussed that this is the variance of z, we already know. So this expression, so this now reads like e raised to j, this is of course mu z, omega minus half sigma z squared omega squared. What is this the expression of? Anyone? No? This is a typical normal characteristic function. So what do we conclude? The first conclusion is what? Z is normal, because the characteristic function of Z looks like normal. Look at here. From here, if you look at Z x u, that's e raised to j mu x u minus half sigma x squared u squared, right? Put v equal to 0. So you get this term and this term. So this is the way a normal characteristic function looks like. A normal random variable with mean and variance. That's exactly the way this looks like. So we conclude that Z is normal. So first conclusion is here. This is, instead of writing this, I know Z is normal with the mean mu Z and variance sigma Z squared, right? So if Z is normal, what about W? Anybody? Also normal. So this is normal with the mu Z and variance sigma Z squared, and this is normal with mu W and variance sigma W squared. What is mu W? Anyone? Expected value of W is C mu x plus D mu y. And what is sigma W squared? Anyone? We went through all this earlier, right? So that's C squared sigma x squared plus CD rho x y sigma x sigma y plus D squared sigma y squared. Okay. So these two answered. What is not answered is what is the joint characteristic function. Any questions so far? So look, without doing any integration or mapping and line and this and that, we solved two problems, or at least one problem. Any linear combination of two jointly Gaussian random variables is Gaussian. Yes? Any linear combination, not just x plus y or x minus y. You could put 0.5 here and 10 here, it doesn't matter, or minus. So that's a big sweeping statement, right? No line, no integration, right? So I am asking a more greedier problem. What is the joint density function of Z and W? So this is what is being asked. Look here. But I'm going to work with the characteristic function. So let's go. So characteristic function of the joint characteristic function of Z and W is what? So this is your U, this is your V. So this is e raised to j Z U plus W V, right? Also this is going to be, let's substitute for Z. Z is what? E raised to j ax plus by plus what? Yeah, cx plus dy multiplied by omega 2, right? So collect all the x terms together. So this is expected value of e to the power j, then what? So look here, this is, if you read this as u, this is of the form e raised to j ux plus vy. Look here. E to the power j ux plus vy, that's this. So I am going to plug into this expression the correct values of u and v, right? So this is, u is what? A omega 1 plus b omega 2 multiplied by mu x. plus V is anybody? Sigma x squared u squared, right? So u is, you need to substitute here, minus 2 rho xy sigma x sigma y u v. V is here, u is here, plus sigma y squared v squared. V is here. So if you substitute here, you can rearrange the terms. Look here, this rearranging is easy. A mu x plus b mu y multiplied by omega 1 plus c mu x plus d mu y multiplied by omega 2. So you can see that these are the means of minus half. So look here before you write it down. See, look here, u. When you expand the u, you are going to get omega 1 squared term, right? Omega 2 squared term. Then you get omega 1, omega 2. The same thing here, omega 1 squared term, omega 2 squared term, omega 1, omega 2. Same thing here. So I want, you can just clearly see that you can write this as this way, right? You should be able to see this much, right? So there is some work involved. So already you see, if this is true, you see this form, doesn't matter what these values are, which you can go home and fill up. That form looks like this. Look at my argument. See, I'm not doing any integration, I'm just arguing stuff. That form looks like this form. See, there is a quadratic term of u squared, uv, b squared. That's exactly the same, no more, no less. Initially there is linear terms with the constants. So this is the form of two jointly Gaussian random variables. So what do you conclude here about these two? They are also jointly Gaussian. That's the conclusion. The rest are details. Okay, so the important result are these are ZW are also jointly Gaussian. So then of course if you argue that much, look here, whatever is the first term must be the variance of what? Variance of the first random variable, which is z. So this must be, you find out all the terms, this must be the variance of z, this must be the variance of w. Then this term you should be able to write it like this, right? Then what is remaining, this whatever is going to be the correlation between z and w. So of course you know the variance of z. Look here, variance of z and variance of w are there. You can mentally see that is going to be true because when you expand you get, look here, when you expand u squared you are going to get a squared sigma x squared plus c squared sigma y plus b squared sigma y squared plus from here you will get 2 rho xy. I guess this is plus, right? It's plus here. So plus, so you need to, so whatever is the term coming here, from there you can extract the rho. That's what I'm trying to say. We can also do this directly, which I will do in a second. So you know the term that is going to come here is covariance of z comma w, right? Right, that's the term that's going to come here because this is the covariance of x comma y. Once you decide that, once you argue saying that this is jointly Gaussian form, then this is going to be covariance of covariance of z comma w. So which we can do directly here. So what is the conclusion? So let me write down the answers. This you know the answer. This is what? They are jointly Gaussian. So I can write this is Gaussian with some mean, some two means, and the two variances, and some correlation coefficient, which I am going to find out in a second. So because we concluded that they are jointly Gaussian, we know the values of mu z is here, right? Mu z is a mu x plus b mu y, right? And mu w is c mu x plus d mu y, and sigma x squared, sigma z squared is a squared sigma x squared plus 2ab rho xy sigma x sigma y plus and how about the variance of w, which is already here, right? So the only thing that is missing is the fifth term, but we know that this term is what? Covariance of z comma w divided by these quantities, you know, right? I just have it here in terms of a, b, c, and etc. This is sigma z squared, and sigma w squared from there is c squared sigma x squared plus 2cd sigma rho xy sigma x sigma y plus d squared sigma y squared. So let's concentrate on finding covariance of z comma w. So that's going to be what? What is the definition? Expected value of zw. These quantities you know, right? Or we can write it another way also. So this is going to be expected value of z minus mu z multiplied by w minus mu w. So the substitute for z. Z is what? Ax plus by minus this quantity. So what do you get? A multiplied by that's one term. So this multiplied by what? W minus mu w. So you can do it mentally. What is it? C multiplied by? Plus? All right, now you see you multiply this with this, you have four terms, right? So what is the first term? AC multiplied by x minus mu x squared expected value. What is that? And look at the cross term. This multiplied by this. So that is AD plus BC. This multiplied by this. What do you get? X minus mu x multiplied by y minus mu y. What is that? This is expected value of x minus mu x multiplied by, what is this? You are tired, you cannot be more tired than me. This is covariance of x comma y, which is rho xy sigma x sigma y. Plus what is the last term? This multiplied by this. Very good. So that's the covariance of, so that you plug it in here, divide by these quantities, you get the rho zy, right? So this is the covariance. So I have given you all the 5 expressions. So let's summarize, see whether you will remember this. If you take any two linear combinations of two jointly Gaussian random variables, what is the first conclusion? Those two linear combinations are both individually Gaussian, they're all, but more importantly, they are jointly Gaussian. Are they independent? Maybe, because it depends on rho. You find rho. How will you find rho? You have to go through these steps. You need to find the covariance. But you look at there. If you don't need to remember this expression, but everything is expressed in terms of sigma x squared, sigma y squared, and rho xy. So you compute this quantity. If this turns out to be 0, what is the conclusion? They are independent. If this is not 0, then what it is? They are dependent, right? So two linear combinations of jointly Gaussian random variables, any two linear combination, nothing special, are always jointly Gaussian, and they are also of course marginally Gaussian, and their covariance is given by this, the correlation is given by this. So here is the last piece of this. Can you make this, can you adjust the, remember you have freedom in A, B, C, D. Can you choose A, B, C, D so that you can make these new random variables independent? What will be the answer? If you make them independent, what happens to the covariance or correlation? Which covariance? C and W. Remember, there are too many covariances going on. There is covariance of X and Y which is given. X and Y are not independent to start with. Rho xy is 0.1, whatever. But look at this, there is a lot of freedom, A, B, C, D. In fact, you don't need all of them. Even if your A, B, C are given, you can fix it, you can select D by equate this to 0 and solve for D. Then you can make the, so two random variables can be made independent by simply, you compute the correlation between these two random variables and put it equal to 0. So let me give you a simple example. Let's say you take one combination is x plus y, the other combination is, or I will leave here A. So I put C equal to 1, D equal to 1, B equal to 1. So the question is, can I make these two random variables independent? Hello? How will you solve it? So so to start with, they are jointly Gaussian, marginally Gaussian. So all I need to find out is their covariance, which is here. So look here. So I'm just going to make B and D are 1. So let me write down this expression in one line. So this was rho xy, sigma x, sigma y, plus what was it? BD, right? Sigma y squared. So in our case, the covariance of xy, only A is non-zero. So this is A sigma x squared. B is 1, C is 1. So this is, what is it? 1 plus A multiplied by rho xy, sigma x, sigma y, plus B and D are 1, sigma y squared, equal to 0. And you solve for A, right? So you will see A is what it is. What is it? Covariance of Z and W. Yeah, right. Yeah, this expression equal to 0. That means rho of Z comma W would be 0. That means these two random variables are independent. You can only conclude that because we have already concluded Z and W are jointly Gaussian, right? And so look at this case. So if X and Y are xy are like this. Xy are 0 mean they have unit variance, or take the variance to be equal, sigma squared, and they have some correlation which is not 0. So x and y are not independent, right? What can you say about these two random variables? Anybody? They are jointly Gaussian, right? Why? Any two linear, we have a theorem, any two linear combinations of jointly Gaussian random variables are Gaussian. What is the, my question is, what is the correlation between these two random variables? Anybody? So look here, A is 1, so let's look at the covariance actually, covariance of Z comma W. In fact, you can plug it in directly, that expression is what? Expected value of ZW minus mu Z mu. What is mu Z mu W? Anybody? Mu W is what? Mu Z is? Oh, so this term is gone, both are 0, right, because it is 0 here. Even if they are equal, this will be gone. Okay. So even if you had mu here, this would be 0, right? So expected value of Z multiplied dot W is the same as what? Z is what? X minus Y. So this is x squared minus expected, which is? So what is it? Anyone?
Sigma x plus mu square. Sigma mu square is 0. Sigma square 0.
Why 0? Because this is sigma squared, this is sigma squared. Sigma x squared minus sigma y squared, but I made them equal. So this is 0. Covariance is 0, so the correlation is? So they are independent. It doesn't make any sense generally. Look, why should x plus, you could say they all depend on the same random variable, but that's the peculiarities of statistics and probability, right? So actually these two random variables are independent. So if you have jointly Gaussian random variables with equal variance, and if you want to generate independent variables, this is the right way to do it. There is nothing more, nothing less. Now you could, why don't you try to redo this problem? Suppose this is 2 here. See, try to find out the right combination so that they are independent, etc. Okay. So I'm going to leave it to you.